Guys, and welcome to second year higher level maths. We are actually starting with kind of the end of last year's course. We didn't quite get it finished because of the end of this chapter and another chapter left on the first year plan. Now, this is unfortunate because we're actually in the middle of a chapter. So we started this chapter 24, and it was the last thing that I put on your exam in June or May. So we talked about quadrilaterals as being four-sided shapes. You might need to go back, I suppose, and have a look at the last video I gave you before you did your exam. It would just help you, just kind of remind you of everything. But these are my notes, so this is what I went through with you. We went through parallelograms, we went through different types of parallelograms and important points about their angles and lines. And we did theorem 7 and theorem 8. So we learned that in a parallelogram, like my little picture over here, opposite sides are equal and opposite angles are equal. And we learned that the diagonals of a parallelogram bisect each other. And I think up here we learned that bisect was to cut in half. That's what bisect meant. Okay, and then I did a couple of examples going through different questions. Okay, so I have the link there, which means I sent it to you. So I think it would be a really good idea to maybe watch that first. It's probably only like a 10-minute clip before we go on to this. So the next thing in this chapter is similar triangles. Okay, you can see just down below there, it's highlighted. So similar is an unfortunately kind of, I don't know, it's not a specific enough word, I think is what I'm trying to say here. The other word for similar is equiangular, which I like better because it's very specific. Okay, and if we break this word apart, the first part, equi, okay, so that's referring to equal. And then the second part, angular, is referring to angles. So essentially what this means is equal angles. Okay, so if you have equiangular triangles, then you have two triangles with equal angles. Yeah? Similar means the same thing. But again, it's just similar. It's just such a normal word that we use all the time that applying it in a mathematical term, people tend to forget what it means. So unfortunately, you're going to have to remember it. So the exam papers will use the word similar, and you need to remember that similar relates to equiangular, and then take the word equiangular apart. Equi means equal and angular, angles. Okay, so similar triangles are equiangular triangles, which means they have equal angles. Okay, so if you look at this little picture I have here, we have a 50-degree angle over here, and that matches this is an important word, corresponding 50-degree angle over here. So we say they are corresponding angles. Here I have a 70-degree angle in the little triangle, and I have a corresponding 70-degree angle in the big triangle. And then here I have a 60-degree angle in the small one and a corresponding 60-degree angle in the big one. Okay, so those two triangles are equiangular because the angles are equal. One thing you should note about similar or equiangular triangles is that while they do have the same angles, and they must have the same angles, they are not the same size. Generally speaking, one is an enlargement of the other. The writing has slowed down to get back up to pace. So equiangular or similar triangles have the same angles, but they are not the same size. And generally speaking, one is an enlargement of the other. So they're identical. It's just like one of them was bumped up to ×2 or ×3 or ×4. It's just a bigger version of the little triangle. Yeah? You don't necessarily need all three. Okay, so if I glance at these two here, I have a 40-degree angle here and a corresponding 40-degree angle here. I have a 60-degree angle and a corresponding 60-degree angle here. And that is enough for me to reach the conclusion, this is a light bulb and me reaching my conclusion. Do you remember how good I am at drawing? So light bulb moment, I can tell even after just seeing two that they're similar. Now, how come I can do that? How come I can say, even after only seeing two, that I know all three angles are the same? Okay, I hope you're telling me. I really do. But because one of the theorems we learned was that the three angles of a triangle add up to 180. If I add up 40 and 60 in the little triangle, I'll get 100. And then if I subtract 100 from 180, I'll get 80. So I know that this angle has to be 80. And because these two are the same, to get this angle, I'll be doing the same maths. So I'll get 80 again. Yeah? So if you have two angles, so an angle and then its matching correspondent, and another angle and its matching corresponding angle, you know the third one has to be the same. So that means after only two angles, you can conclude that they're similar. Is that all right? So that's what a similar triangle is. That's what they look like. They will always stand out because they're almost like it's always a little enlarged. So that's why they stand out on a paper. The theorem relating to this, it sounds a bit abstract, but it's actually really easy. As in, the maths of it is easy, but it sounds weird when you learn it. So if two triangles are similar, remember then that word. We can always sub it for equiangular. Okay, so when two triangles are similar, their sides are proportional in order. Now, how horrific does that sound? Their sides are proportional in order. Okay, let me explain what on earth they're talking about there. Okay, so here we have two similar triangles. Okay, how do I know they're similar? Now, can I zoom in a little on this? Yeah. Okay, so we learned a bit about angle notation at the end of last year, because so you can see this one here has just the one little line, and here the corresponding angle has just the one little line. So what they're saying is that angle here at B and the angle here at E are the same. Okay, so the angle at B is the same as the angle at E, right? So now let's look here. If you can see here, this has two little lines. And over here we've two little lines. So what are they trying to tell us? They're trying to tell us that the angle at A is the same as the angle at D. And then the one at the top, we have no lines, just a loop. No lines, just a loop. So what are they trying to tell us? They're trying to tell us that the angle at C is the same as the angle at F. So essentially what we have is we have this angle is the same as the corresponding angle. This angle is the same as the corresponding angle. And this angle is the same as the corresponding angle. So what we have here are similar triangles. Yeah? And now I'm going to erase all that mess there. But so the fact that the three angles are the same in both triangles mean we have similar triangles. According to theorem 13, if two triangles are similar, which we have now established that they are, their sides are proportional in order. Okay, so what that means is that if you pick a side, right, so I'm going to pick this big long side here, AC. If I know what the length of AC is, and I divide it by the corresponding side in the other triangle, okay, so this triangle here, or sorry, this line here goes from the double angle, the one with the double line, to the one with no line. And the corresponding side, this one here, goes from the one with the two lines to the one with no lines. So these are corresponding. Does that make sense? So if I put AC over DF, okay, if I put the corresponding sides over each other, that will be the same answer. So I've created a fraction. That will be the same answer as if I put any other corresponding sides over each other. So here, this line here goes from the no line to the single, and the corresponding one here, no line to the single. So they're corresponding. So if I put CB over FE, I should get the same answer as if I put AC over DF. Or the last one, if I put AB over DE, that should also give me the same answer. So if you create a fraction using corresponding sides, and the in order part refers to the fact that, see the way my top line in each one, so my top line, my top line, and my top line, they all come from the big triangle, and all my bottom lines come from the small triangle. That's what the in order part means. Okay, the proportional part refers to creating a fraction. So you're creating a portion. So, you know, like if you were talking about like a pizza or something, you'd say like a half of the pizza or a quarter of the pizza. Okay, so that's what the proportional thing refers to, that you're putting one over the other. You're creating that fraction. And in order refers to the fact that if you're putting the big triangle on the top of the fraction, that has to hold. So you can't switch and all of a sudden put the little triangle over the big triangle. Okay, so now I know that's complicated, and while technically this falls under in the ordinary level book, there is absolutely not a chance in hell this would be asked on an ordinary level paper. Okay, so if two triangles are similar or equiangular, if they have the same angles, their sides are proportional in order. So that means you can take one side from the big triangle and put that over the corresponding side from the little triangle and create a fraction. If you then take another side in the big triangle and put it over the corresponding side in the little triangle, those fractions will be the same. Okay, that's what it's saying, that those fractions will be the same. They will be the same. They will be proportional. They will be the same. So you might find that when you do the first fraction, you get 4 over 2. And when you do the second fraction, you get 10 over 5. But they're the same thing. Because what is 4 over 2? That's 4 divided by 2, which is 2. And what is 10 over 5? It's 10 divided by 5, which is 2. So that's what they're saying. They will be proportional in order. So providing you keep the order the same, as in big over little, they will be proportional. So they'll be different fractions, but they will amount to the same. They will equal the same thing. Okay? So now, I know that's a lot, okay? And as always, the example will help to cement the explanation, because it's hard trying to explain it when there's no numbers. So hopefully when I do the example, it will be a bit clearer. But obviously, because this is a recording, you'll be able to rewind and go back over that explanation a few times. Okay, and if you don't understand, you know, the difference between this and lockdown, I suppose, is that if you don't understand, you do have a teacher there to ask. So do ask, but I would suggest that you listen to this and just wait until we've done an example or two, okay? Because it's hard, it's a challenging one to explain, and even the language in it is funny. Proportional in order is a weird language, but I swear it's not as hard as it seems. Okay, so trust me for another like 5.5 minutes. Right, so here's an example. So find the length of the side marked X in the following pair of similar triangles. So they're telling us they're similar, right? And they're also backing that up with the angle notation. So here you have your angle here with no line on it, so that matches this one. Okay, so we've this one matching this one. This one has a single line, so this one matches your single line here. And then this one with the double line matches this one with the double line. Okay, so they told us it was similar, but we can also see from what we know about triangles and now similar triangles that they are equiangular. Okay, so if they're equiangular, then we know, according to the theorem, that they are proportional in order. Okay, so I'm going to pick a side. Now, the only reason I'm picking the little triangle is because it's on the left and I read from left to right. Okay, it doesn't matter if you go the other way. So I'm going to pick the little triangle and I'm going to start with X. Okay, and I'm going to make that the top of my fraction. What is the corresponding side in the other triangle with X? Okay, so hopefully you can see that it's 8. So X and 8 are corresponding. So I create a fraction with them, and I need to make a mental note that what I've done here is I've put the little triangle on the top and I've put the big triangle on the bottom, because I'm going to need to be consistent with that. Okay, so now I've created my first fraction, and that should be the same or proportional to any other fraction that I create, providing I keep the order the same. So I have another side in the little triangle, and remember little needs to be on top. So I put my 5 on top. The corresponding angle to that is the 10, so I put that on the bottom. Now, the fact that these are similar means that these two fractions should be the same. Okay, they should be the same fraction. Now, I'm sure a load of you, knowing you guys, already have it. But I'm just going to show you the maths of how to do it because sometimes these are not quite as clear. Okay, so when you have a fraction on the left and a fraction on the right and an equals in the middle, what we use is cross multiplication. So I multiply this one by this one, and I multiply this one by this one. And the purpose of these multiplications is to get rid of the fraction. I don't want the fraction. So essentially, I'm going to actually change my arrows because what I want you to do is not multiply down. I want you to multiply up. So I want you to multiply that 10 up by the x, and I want you to multiply this 8 up by the 5. Okay, so hopefully you remember this. We did a bit of this last year. So 10 multiplied by x, that is a number and a variable, so we can't actually do anything. We just do 10x. So 10 multiplied by x is just 10x. I'm going to write down my equals, and then I have 8 multiplied by 5, and 8 multiplied by 5 is 40. Okay, now there is a multiplication, an invisible multiplication sign between the 10 and the x. So in order to separate these, I need to do the opposite of multiplication, which is to divide by 10. So the x is being multiplied by 10. To remove that, or to separate and move the 10 away from the x, I need to do the opposite of multiply 10, and the opposite of multiply 10 is divide 10. But if I do that over here, I need to mirror and do that over here. Okay, remember you always have to do it on both sides. So now the multiply by 10 and the divide by 10 will take each other out, and I'm left with my x, and 40 divided by 10 is 4. Okay, and you might have figured that out because 5 is half of 10, so whatever x is needs to be half of 8. Okay, because they are proportional. Okay, so that's essentially what you do. You create a fraction by combining one triangle with the other triangle, either little over big or big over little. It doesn't really matter. And then you create a second fraction doing the exact same thing, so keeping the order the same. So if it was little over big the first time, you need to stick with little over big. The maths, the algebra of it is to cross multiply. Okay, I realize probably most of you saw that, oh, it's just half, so the answer is 4, and that's fine. But I always like to teach you maths that will carry no matter how difficult the sum gets. And that's why it's important to know that when you are doing these similar triangle proportional in order questions, that the way to solve it is with a cross multiplication. Now, for a question like that, like literally, if you got that, you won't, but if you got that question on a higher level junior cert paper, it would be fine to just say x is 4. They would expect you to have that level of maths to be able to see that it's half. But most of the time, it will not be that easy to solve, and you will need to be able to cross multiply. Okay, so I'm giving you maths. I mean, that's my job. I give you maths that arms you no matter how hard the question gets. Okay, so I know that cross multiply might seem like overkill, but I promise you, you will need it at some point. Okay, so I'm going to keep going and do another example. Where is that example? Oh, here, actually, we look at this little one at the bottom. Sorry. So this is still your Active Maths 1 book, but you will have to get Active Maths 2 because we'll be moving into it fairly quickly now, to be fair. Why is that not working? Yeah. Okay, so yeah, you need to get Active Maths 2. I think you need to know how it works. I think you need to buy it so that it ends up on your iPad. But yeah, like I think with this chapter, I think we've one more chapter to do in Active Maths 1, and then we're going into Active Maths 2, so you'll need it fairly soon. Right, so let's have a look at this. So they're asking us here, is the triangle X, excuse me, YZ, which is the one here on the left, similar to triangle PQR, right? So we don't have any angles, so we can't prove whether they're similar or not just based on the angles, which is what we've done so far. But we can use the theorem, and the theorem said that if they're similar, then their sides will be proportional in order. Yeah? So let's have a look. So here's 2. I picked 2 at random, and remember, 2 is in the little triangle, so I'm going to put 2 on the top of the fraction. I need to find the corresponding side in the big triangle to 2, and 2 corresponds to the 4. So 2 over 4. 2 over 4 is a fraction, obviously. It's a proper fraction because the top line is smaller than the bottom line. And it is not in its simplest terms, but I can easily put it into its simplest terms. And it's a half. Yeah? Now I'm going to pick a different side. So I will pick the 3. Again, I'm starting. I have to keep it in order. So I'm starting with the little triangle again. And this time the corresponding side is here, which is a 6. Again, that's a proper fraction where the numerator is smaller than the denominator, and I can simplify it to a half. And then one more. Start with the little triangle again with a 4 and put it over the big triangle of an 8, and I can simplify that to a half. So if these 2 triangles are similar, then their sides should be proportional, providing I keep the order right. And I did keep the order right every time I started with the little triangle. And were they proportional? Yes, they were. All of those fractions were a half. So they are proportional. Okay? Now, there was one about a lamppost and a building that I want to do. Yeah, okay. So now, I know you can see that picture, but if you were given this in an exam, you would not usually be given the picture. But anywhere in geometry or trigonometry, it's really important to, oh no, what have I done? It's really important to draw, okay? It makes it so much easier to do the questions if you draw. And so they've given us it here, they've given us the thingy here, but if they've given us the diagram here, apparently I can't multitask, but if they didn't give you the diagram, it would be fine because you would just draw it. Okay, so we have a building, clearly, which casts a shadow of length 10 meters. Here it is here. At the same time, and I'll come back to that, a 3 meter high lamppost, so I think that's your lamppost there, casts a shadow of length 2 meters. 2 meters. How tall is the building? Okay, so essentially we want to know what length is that line there. So we'll call that X because we don't know it. Yeah? Now, do we know these triangles are similar? Okay, I think it's fair enough to assume that the lamppost was put up straight, as in vertical, and the building was built straight, as in vertical, which means these angles here are 90 degrees. Yeah? So they're the same. Now, so all we have to wonder is this the same? And is this one the same? Okay, now there is something in the question that tells us they're the same. Okay, again, if I was in class, I'd be waiting patiently to see if anyone came up with it, and I've no doubt you would. This is a question about shadows, and they mentioned that these 2 little snapshots were taken at the same time. Okay, so what we're talking about here is where was the sun? Okay, the fact that this was taken at the same time means the sun was at the same angle on both of them. Okay, now that's very hard assumption to make for junior cert at all. Never mind doing it in second year. So that's tough, right? But these triangles are similar. Okay, and they're similar because they both have this 90-degree angle, and the sun was at the same height in the sky when it shone on the lamppost and the building, meaning it would cast a shadow at the same angle. Okay, so obviously if this, I don't know if this is obvious, but if the sun is like up here direct, nice red sun, was up here directly above it, you wouldn't get much of a shadow at all because the sun would be able to shine kind of right down here. And then as the sun moves around, obviously it casts more of a shadow because it's been blocked by the building. And then when the sun goes really low in the sky, kind of just before the moon comes out, you get massive shadows because the building is blocking a lot of it. Okay, so that's more science than maths, really. But the fact that it says that we're talking about shadows and that both of these were taken, I know they're not photographs, but both of these snapshots were drawn at the same time, then you would have the same angles because the sun was at the same height in the sky. Okay, so we can assume these are similar. And if they're similar, then their sides are proportional in order. So I'm going to pick 3 in the little triangle. So again, I'm starting with the little triangle. And I'm going to put that over the corresponding side in the big triangle, which in this case is the building. So that's X. And that should be the same as the 2 in the little triangle over the 10 in the big triangle. Okay, so again, you can probably figure out what X is, but we're going to go through it. So I'm going to take the X and I'm going to multiply it by the 2. And I'm going to take the 10 and I'm going to multiply it by the 3. Okay, so 3 multiplied by 10 is 30. I'm going to copy down my equals. X multiplied by 2 is 2x. We always put the number first, so you can write x2 if you want, but that's just unusual. Here the x is being multiplied by the 2. So to isolate, remember we have to isolate. I don't think I used that word the last time. I definitely used it last year though. We want to isolate that x. So to isolate the x, we need to remove the 2. And to remove the 2, we need to do the opposite of what is currently happening. So at the moment, the x is being multiplied by 2. So we are going to divide it by 2 and that will cancel it out. But if you divide by 2 over here on the right, you have to mirror that on the left. So now my x is isolated and 30 divided by 2 is 15. So that building is 15 meters tall. Okay, so that's similar triangles. You'll have a few questions to do in class, and hopefully that the idea of that would be to iron out any problems you're having. I mean, I know this theorem is tough, but I think it should. Hopefully, I've explained it. Hopefully, I've explained it well enough in the language of proportional in order. So the proportional refers to the fact that when you create those fractions will all be the same when simplified. So like here. So the fractions themselves are not necessarily the same, but when you simplify those fractions, then they're the same. That's the proportional part. And the in order part is the fact that you must, whatever triangle you start with as the numerator, it must consistently be the numerator. So if we look at the little triangle here, it has 2, 3, and 4. So my numerators are 2, 3, and 4. And if we look in the big triangle, it's 4, 6, and 8, and my denominators are 4, 6, and 8. So you can never swap and change in the middle because then you will lose the order, and as a result, proportionality won't work. All right. So yeah, that's it. So, watch the explanation as many times as you need to, and we'll pick a few questions from here. A few nice straightforward questions to get you going. But you are fully fledged higher level students now, so definitely a few challenging questions to get your brains working properly. So do a few of the simple ones. Make sure you understand what you're doing, how to create those fractions, and then we'll try some of the slightly more challenging questions. All right?